Hello everyone. Today we are going to learn 6.4 Green's theorem. All right. So when do we use Green's theorem? And hold on one second. All right. So in order to turn hard line integrals into easier double integrals, we are using Green's theorem. And to compute the area using vector fields and to study circulation and flux inside the region. All right, so we have a learning objective. So we have a circulation and flux. Yeah, so circulation means we measure how much a vector field tends to move around or spin along the path. And flux measures, can you read? This is too light. Measure how much vector field flows along the curve. All right. Okay. So let's do circulation form first. So basically, we need to think measure of rotating. Yeah. Counterclockwise. All right, so Green's theorem, circulation form, let D be an open, simply connected region. So this region, right? And open means not include the boundary itself. So they mentioned that this inside, yeah, not include the boundary here. Okay, now we have a curve C, this C curve, right? So it's a piecewise smooth, simple closed curve, oriented counterclockwise, right? So oriented counterclockwise, going this way. Okay, then we have a vector field. Then we learned from this one line integral last time. Then we have the formula. So the equation, the function in the vector field, yeah, P, we are using integral respect to x, and we are using the function q, and then integrate with respect to y, right? Okay, this one turns into double integration, and then this one was the curve C, then they changed that, double integration of region D, and then look, we're using partial derivative with respect to x from the q equation, q function, right? And then look, we have p equation and the partial derivative with respect to y. Yeah, it's okay. So let's do this example. So we want to calculate the line integrals given, right? Oh, this is hard, right? So we are applying the Green's theorem. So where C is a rectangle with vertices is 1, 1, 4, 1, 4, 5, 1, 5. So I drew the rectangle here and then oriented counterclockwise. Yeah. So going this way, we start 1, 1, counterclockwise, right? That's oriented, right? Counterclockwise. All right, so we are using the Green's theorem. The theorem formula, right? Okay, so since we want to partial derivative with respect to x first, so we have a q of x. No, q, which is y minus 3. Then we want to partial, we want to derivative respect to x, right? What do you get? So we have a 0, right? What about the p? So we have p x squared y, right? Now we want to derivative with respect to y. Then x is the constant, right? So x squared, we keep the constant. And then times 1, right? Okay, now let's do this one. Okay, so we want to derivative with respect to x first. So look, this is x-axis, y-axis. So x start to 1 to 4, right? And then y start to 1 to 5. Can you see that, right? All right, so y equal to 1 to 5 and x equal to 1 to 4. Then we have this one, which is 0, right? So we have 0. Oops. Zero minus. We have a partial derivative with respect to y, so we have x squared. So we have x squared there. Then dx dy, yeah? Okay, now we have just a negative x squared, right? We want to, let's do just one step, right? So do first, there is no y, so no need to treat y as constant, right? So we want to integrate respect to x. So negative x squared, what do you get? So we have y equal to 1 to 5. And then negative x to the third power over 3, right? From x equal to 1 to 4. Okay. So we do evaluate. So 4 to the third power minus 1. Can you please calculate? Yeah. So we have a negative 21 dy. Good. Okay. Then integrate respect to y. So we get negative 21y. We want to evaluate from 1 to 5. So there will be negative 21, 5 minus 1. So we get negative 84. Okay, so we have negative means, this means if we have a positive, then counterclockwise, right? So negative means clockwise orientation. Good? Okay, so we have a second example. Calculate work done on particular by force of field. There is. And then particle transfers, right? Transfers. Let me check the spell. Yeah, one S is missing. Traverses here. Circle x squared plus y squared equal to 4. So radius equal to 2, right? So I draw the circle here. So starting point, end point 2, 0, right? So that means close. All right. Let's do this. So we have the form work done. Let's writing out. So W work done, we start with that. Then line integral, right? So we have P dx, right? So P in the case, y plus sine x dx and plus q dy. So we have a q, which is e to the y. I'm using this one, minus x, right? So e to the y minus x, that's dy. Now, Green's theorem said that we can make a double integration with the region D, then Q sub X minus P sub Y, right? And dA. Okay, now let me write down one more time P and Q here. So note Q xy equal to e to the y minus x. We want to respect derivative with respect to x. What do you get? -1. Good. So it's -1. We have p, then y plus sine x. Then we want to derivative with respect to y. Also 1, right? Just y there. Okay. Now let's do this one. So we want to find D, region D, and Q sub X, we have a -1 minus P sub Y, which is 1, right? And then dA. Yeah. Okay. Now, what do you get? -1 minus 1. So we are doing, you cannot see. Okay. So we have -2, reason D, -2 dA, right? All right. So why we don't, it's hard to say, why we don't set it up, the limit, -2 to 2, positive -2 to 2 for the y, right? Because the reason is the circle is not the square, right? So if we have a square, then yes, we can set it up that way, right? Make sense? Why we don't set it up limit as earlier, right? Okay, now what's the dA means? We know that in the double integration, so that's the area of region D, right? Means area. Okay, so this is circle, then what's the area of circle? Which is 2 pi r, right? Pi r square, right? Okay, so there will be, let me do it. So not anymore. So there will be, we can calculate -2 pi r square. That's area of region D, which is the area of a circle, right? So r in the case, we have 2, right? So r square, which is 2 square. So we have -pi. So -2 pi 2 square, which is -8 pi, right? So what this mean? Negative. Yeah, we had a clockwise orientation, right? Okay, so we had a clockwise orientation. But let's take a look here. The Green's theorem says that the curve orientated, right? Oriented, not tated, oriented counterclockwise, right? So we have to have the curve start the counterclockwise, right? In order to use Green's theorem, so simply connected the curve closed and the orientation is counterclockwise. Make sense? Now, even this says that oriented clockwise, counterclockwise, sorry, counterclockwise. Yeah, that's why we have to, we can apply the Green's theorem. Yeah. All right. So everything turn became the clockwise orientation. That means the vector field push into clockwise direction. Yeah. So let me write down. Okay, so I wrote down the vector field may push in the clockwise direction, or we might think the field is spinning the opposite way. Okay? Okay, so I brought the picture from the textbook so we can realize that the spinning goes the clockwise opposite way, right? All right. Next, we have Green's theorem, flux form. So flux form, think measure of a flow, right? Okay. We did this one before in the 6.2 line integral, right? So in the last question, we did that. All right, so everything is the same as circulation form. Okay, then the Green's theorem, the formula change here, right? So we had a q sub x minus a p sub y earlier, right? So this one, p sub x plus q sub y. Yeah. Okay. Now, the example applying Green's theorem for flux across the circle. So we have a vector field, we have x and y. We want to calculate the flux across the curve C, which is in that case, not unicircle, it's a circle, right? Okay. So let's set it up. So there will be integral of vector field dot product with the unit normal vector. Yes. So then we can have that Green's theorem, which is P of x plus Q of y dA, right? Okay. Let's do this one. So note, we have a p of x and y equal to x. Then we want to respect derivative with respect to x. Then we get 1, right? Now we have a q equation, q function. We have y, and then we want to derivative that respect to y, right? Oh, you cannot say. So it's also 1. Okay, now, so we have reason D. So what do you get? We add it together, so we have 1 plus 1 dA, right? Okay, then we had the experience 2 dA, then what's the dA means area of circle, right? So there will be 2 area, ooh, circle. So pi r squared. Okay, so we will have 2 pi r squared in the case. All right, so let's take a look. So they don't say anything about the r and then the equation. They just show us the picture, right? So if we want to answer from this picture, yes, we can say that r equal to 2 looks like a 2, right? So this is a 2, yeah? So we can just using that r equal to 2. So it's the same as 8 pi, but in general, they don't give us the equation. They don't give us the r. So we can just leave as a general answer, all right? Okay, you cannot see. So if, let me write down, r equal to 2, then the answer we get 2 pi, 2 square, which is 8 pi. Yeah. All right. Okay, so let's do this example. Let S, so normally they put the C, right? But in the case it's S, triangle with the vertices 0, 0, 1, 0, 0, 3, right? Oriented clockwise, it's different, right? So normally we have counterclockwise, but in that case it's clockwise. All right. Then we want to calculate the flux, yeah? But then in order to apply Green's theorem, we have to have counterclockwise orientation, right? Okay, then how do we make counterclockwise orientation? So we just put the negative sign. So let me show you. So we have the formula. So curve C and then vector field and then dot product with the normal vector, right? And then the S. Okay, then we want to make a negative in order to make counterclockwise orientation. All right. So we're using C. So actually negative C, right? And then F, the normal vector, and ds. Okay, now since we have counterclockwise orientation, we can apply Green's theorem, right? Okay, so that will be negative reason D. So we have the formula say that P sub x plus Q sub y dA, right? Okay, then let's find out. Can you see? I need to see the function. So note P of x, y equal to x to the second power plus e to the y. We want the derivative with respect to x. What do you get? Oh, you cannot see. 2x. Yeah, good. How about P of xy? I mean, sorry, Q of xy You cannot see. Let me see. X plus y. Yeah. X plus y. Then what's the derivative with respect to y? Sorry about that. Okay. Then we have 1, right? All right. So we get 2x plus 1. 2x plus 1 dA. Yeah. Okay. Okay, now let's find the limit. So we have x. X is, we have 0 to 1, right? Obviously. But then what about the y, right? So we cannot use 0 and 3 because this is triangle, right? How do we find? Very good. So we want to find this equation, right? So y-intercept, which is 3. So we start with that. Plus 3, right? Then we need to find the slope. Okay, so let's find out from the y-intercept. 1, 2, 3, down 3 over 1. Yeah, so there will be negative 3 over 1 x, which is negative 3, right? I can write it down for you. So we have the equation. So we can use the limit from 0 to that equation for y. Then we need to integrate with respect to y first, right? And then x later so that we can find out the how much for the flux. Yeah? All right, so let's do that. Let's keep continue. Negative x equal to 0 to, you cannot see, oh, you can see. All right, now y equal to 0 to 3x plus 3, right? Okay. Y equal to negative 3x plus 3. And then we have 2x plus 1. And respect to dy, dx, yeah? Okay. Let me write down because I don't see the y, that's why. So do first. That means treat x as constant, right? All right. So this is a constant, so we keep that constant. So we want to evaluate respect to y, then we get the constant and y. Yeah? All right. So we have negative x equal to 0 to 1, 2x plus 1, y. And then we want to evaluate from 0 to negative 3x plus 3. Okay, now negative x equal to 0 to 1. All right, so we have a 2x plus 1 and y, which is negative 3x plus 3 dx. Okay, we do distribute. So we have negative 6x squared plus 6x minus 3x plus 3, right? Okay, so we have negative 6x squared plus 3x plus 3 dx. Easy to integrate, right? So we have integrate respect x. So x to the third power over 3 plus x squared 3 over 2 plus 3x. Oh my gosh. I made a mistake here. So here is 1, not the 0, 1. Okay, so from x equal to 0 to 1, All right, so we will have negative 2, 1 plus 3 over 2 plus 3. Can you please calculate? All right, so do you get the negative 5 over 2? Okay, so we have a negative 5 over 2. What this mean? Let me write down. Okay, so I wrote down some note here. So negative means flux is inward, means that the flowing inward, right, inside. So we knew that this is the vector, so magnitude of a flux, right? And since we have negative, then flowing inward, then positive flux, we can say the flowing outward, right? Okay, we have another note. So clockwise curve orientation makes that normal vector point inward, not outward, right? And then that normal vector point inward, so flux has inward too. Make sense? Okay, then let's take a look here, the picture. So this is a vector field, right? So vector field, look, what's going on? So look, this vector field looks like goes the outward, right? So we can see that, right? Can you see? Yeah. So it's not matter whether vector field goes the outward, even though that since the orientation of curve clockwise. Yeah. So this clockwise makes vector field, sorry, not the vector field, normal vector makes inward so that the flowing goes inward too, because we get the negative flux. Yeah, make sense of the conclusion? All right, so this section is short. Thank you for watching. See you next time. Bye.